Welcome to the Bentley Systems training course, where you will learn how to generate load combinations and specify analysis commands in the STAAD.Pro Analytical Modeler. In this particular video, we will be focusing on invoking a direct analysis according to the AISC 360-16 specification. The AISC 360-16 Chapter C describes the direct analysis method, which accounts for second-order effects resulting from deformation in the structure due to applied loading, imperfections, and reduced bending stiffnesses of members due to the presence of axial load. To incorporate the direct analysis method in STAAD.Pro, we will be focusing on adding the following parameters to our steel structures. We will ask the program to incorporate our second-order effects, including our P large delta and P small delta effects. We will consider the initial system imperfections through the new use of notional loads, and we will adjust the flexural and axial stiffnesses of members using a direct analysis load definition. Keep in mind that this is a nonlinear iterative analysis, as the stiffness of the members is dependent on the forces generated by the load. So let's go ahead and get started with the first step in our workflow, which is to adjust the stiffness of the members as required by this procedure. To do this, we will go ahead and invoke the direct analysis load definition, which will assign the flex and axial parameters to the members in our model. Members listed with the flex parameter will have their EI values factored by 0.8 times your tau factor while performing the global solution, and members listed with the axial parameter will have their EA values factored by 0.80 while performing the global solution. To define your direct analysis definition, we will go to the Load and Definition dialog and highlight the Direct Analysis Definition option. We will then click on the Add button to add the flex and axial parameters. In this dialog, we're going to enter a value of flex of 1. What this does is it basically sets the initial value of your tau factor. Within STAAD.Pro Connect Edition, you have the option to either manually specify your tau factor or perform an iterative solution for tau. For this particular model, we will be performing an iterative solution for the tau factor for each of our load cases, and we will set the initial value for that iteration of tau to be 1.0. To finish this off, we'll click on our Add button. Next, let's go ahead and select the axial parameter. This has no additional data required, so we'll go ahead and click the Add button and then close. Expanding the direct analysis load definition, I can see that both of these parameters will need to be assigned to the members in the model. Now, if I were to take a look at the AISC 360, I can see that applying the stiffness reduction to some members and not others can, in some cases, result in artificial distortion of the structure under load and possible unintended redistribution of forces. Now, for this reason, I'm going to go ahead and assign the flex and axial parameters to all of the members within my model. To do that, I can highlight the first parameter, click on the Assign to View Radio button, and then click the Assign button. To complete this process, I will repeat this process now with the axial parameter. Now, as I previously mentioned, for this particular model, I'm going to ask the program to perform an iterative solution to calculate the tau factor. Now, the program will be able to calculate the tau factor, which is also dependent upon the yield strength of steel. So let's go ahead and pause at this moment and consider what yield strength of steel will be used in calculating that tau factor. If I were to take a look at my materials area and my workflow page control area, I can see that the yield strength of steel will be defined for each of the material parameters. For this particular model, I went ahead and assigned each member with this material property. This is steel 50 KSI, and this is because all of the members within my model are wide flange sections. Now, if you assign a material property where the yield strength of steel is empty, the program will automatically assign a yield strength of steel of 36 KSI. So whenever performing a direct analysis, you do want to review your material specifications to ensure that they have been assigned appropriately. Let's go ahead and return to the loading area, and we are ready to move on to the next step in our workflow, which is to generate our load combinations. Now in STAAD.Pro, we have two different types of load combinations that you can create. You can create a traditional load combination, which has a set of load results which will be combined algebraically to produce a superimposed set of results for post-processing. And you can also create a repeat load case. A repeat load case is a primary load case that will use combinations of previously defined primary load cases. Whenever you're performing any type of second-order analysis, including a p-delta analysis, a direct analysis, or if you have a model that contains tension-only or compression-only members, you must generate repeat load cases to ensure that all of the second-order effects are captured in your analysis results. For that reason, we will be generating repeat style load cases for this model, as a direct analysis is a second order analysis. So let's go ahead and get started. Now this particular model contains dead load, live load, wind load, and IBC static seismic loads that were defined using a seismic load definition. To generate your load combinations, we can come up to the Loading tab in the ribbon toolbar, click on the Automatic Combinations option, and ask the program to generate your load combinations. Now for this particular model, I will be eventually designing this system using the LRFD method. So I'm going to select a code for combination as the AISC 716, and I will select one of the LRFD combination categories. For this model, I will select the strength design where the live load is less than 100 PSF. In addition to that, I also need to make sure that this checkbox is selected. This is what will instruct the program to generate repeat load cases instead of traditional load combinations. Now there's an additional checkbox that would be appropriate for performing a direct analysis, and this is to ask the program to generate notional loads while generating your load combination. Notional loads are basically a portion of the gravity load that will be applied horizontally to the structure. In order to specify this parameter, you will want to calculate your notional load factor. Now, as I mentioned, I will be performing an LRFD design method, and if I were to take a look in the code, I would see that a 0.002 notional load factor would be appropriate for my particular analysis. So let's go ahead and ask the program to include notional loads at this point. Once both of these checkboxes are selected, I can click on the Generate Loads button. Now before I officially add my load combinations to the input file, let's take a look at the load combinations that have been generated, and we will start with this first one. These first four load combinations represent 1.4 times dead load. The load case that's assigned to dead load is load case number 1. In addition to that, it went ahead and added the notional load onto each of these load cases. It basically took the notional load factor of 0.002, multiplied it by the factor of dead load, which is 1.4 in this case, and it's applying it in the horizontal direction as nodal loads. Here we can see this first load combination represents a positive notional load in the x direction. It created a load combination for the notional load in the negative x direction, the positive z, and the negative z direction. And if we were to follow this methodology on down, we would be able to see the notional loads have been added to each of the load combinations. To finish this process, let's go ahead and click the Add button. And then we will click the Close button. Now, automatically, the program is going to consider a notional load factor of 0.002. If this notional load factor isn't appropriate for your particular model for any reason, you can go ahead and manually change the factors in the input file, or you can manually create a notional load case. I recommend creating a notional load case in the reference load area if that's the workflow you're choosing. Now, before we move on to the next step in our workflow, I think it's also important to understand how load combinations are generated when you're using the load combination generators that are installed with STAAD.Pro. To review that information, we can go to the Loading tab in the ribbon toolbar, click on Automatic Combinations, and then Edit Auto Combination Rules. Within the Automatic Load Combination Manager, you can select the load combination generator that you used in the previous exercise. Here I can see that I used the AISC 716 Strength Design Load Combination Generator, and I'll be able to see all of the load combinations and factors that are appropriate for each load case has been defined in this table. In addition to that, if I select the Configuration option, here I'd be able to see how notional loads are considered. So the program will take a percentage of your gravity load and apply it horizontally. In this field here, I can see what it considers as a gravity load. Here I can see that dead load, live load, roof live load, snow load, and ice loads are considered candidates for that notional load factor. We are now ready to move on to the final step in our workflow, which is to invoke the Direct Analysis command. To do that, we will select the Analysis tab in the Workflow Page Control area, and then click on the Define Commands option. Within the Analysis Print Commands dialog, select the Perform Direct Analysis tab. Here you're going to enter your option. Do you want to perform the analysis for the LRFD or the AISD workflow? As mentioned previously, I am using the LRFD method. In addition to that, the program can perform an iterative solution for both your tau factor and your P delta. And you're going to want to enter the number of iterations in each of these fields to perform that iterative solution. Finally, we're going to tell the program whether or not we want to reduce the EI value, which we will go ahead and say yes. What this will do is it will go ahead and grab that direct analysis definition, your flexural and axial parameters, and ensure that they are incorporated in your analysis. And we will also ask the program to perform a tau B iteration. Now, whenever you're performing an analysis according to the direct analysis procedure, I do recommend that you have a copy of that specification available to you to ensure that all of your factors, including your tau factors, your notional loads, and so forth, are considered appropriately. Finally, whenever invoking a direct analysis within STAAD.Pro, the program will automatically consider both P large delta and P small delta effects. P large delta effects are your second order effects induced on a structure due to the movement of its mass under lateral loads. Your P small delta effects are the second order effects caused by displacement of the member between the bracing points. So at this point, let's go ahead and click on the Add button, and then we will click Close, and we can see that that direct analysis command has been added at the end of the input file. Now there's one last thing that we should consider when performing a direct analysis, and that's to ask ourselves the question, is a multi-run analysis needed for this particular model? So let's go ahead and review those scenarios for which a multi-run analysis would be required. If your model contains tension-only or compression-only members, then you will have to analyze each wind and seismic load case individually, and then reset your stiffness matrix before analyzing the next load case. Now, our model does not contain any tension-only or compression-only members, so we don't fall within that scenario. The second scenario, however, where you would be required to perform a multi-run analysis is if you have seismic loads with repeat load cases. So if your model contains IBC seismic loads, and those loads are then referenced in a repeat load case, you will have to analyze each seismic load case individually and then reset the stiffness matrix before analyzing the next load case. Now, we do fall within this scenario. Our model does contain IBC seismic load cases, and those loads are then referenced into repeat load cases. So we do need to analyze each seismic load case individually. Now, in the previous video, I showed how to add those commands through the graphical user interface. For this particular video, we're going to go to the input file to show you another method for which you can add those commands. To access the input file, we'll select the Utilities tab in the ribbon toolbar and then go to the Command File area. The program will ask you to save your model, and then we will proceed on to the editor. Now, what I'm looking for is my seismic load cases, and here you can see I can click directly to that location. Now, I do need to add a perform analysis command after each IBC seismic load case. Here you can see in the input file, you can just start typing, and then the program will offer you suggestions on the command you're looking for. Here, I'm going to add a perform analysis command and then a change command. What the change command will do is it will ask the program to reset the stiffness matrix before attempting the next load case. So let's go ahead and add that command here, and with a quick copy and paste, I can add it after the next seismic load case as well. Now, if your model contains additional IBC seismic load cases, you may need to do this multiple times, and using the input file might be an easy way to get those commands where they're supposed to be. So let's go ahead and exit out of the input file and take a look at how that information was brought over into the graphical user interface. Here I can see that I'm analyzing each seismic load case individually and then resetting the stiffness matrix before the next load case is defined. In addition to that, I also have my direct analysis command at the end of my input file. Now, there's one last command I want to take a look at for this workflow, and that's the setNL command. Whenever you're performing a multi-run analysis and you're introducing additional load cases after an analysis has already been performed, the program is going to need the setNL command. What this does is it goes ahead and tells the program that you need to set aside some additional memory space for information or loads to be added later. To invoke that command, we will select the Analysis and Design tab in the ribbon toolbar and select the Miscellaneous Commands icon. Let's go ahead and go down and use the setNL command. Now, what you want to do here is you want to make sure that you are setting the maximum number of loads to be greater than or equal to the total number of loads in your model. I'm going to set this value equal to 100 and click OK. Now, at this point in my workflow, I'm ready to go ahead and perform my direct analysis. I have incorporated all of the requirements of the AISC 36016. Now, at this point in my workflow, I'm ready to go ahead and perform the analysis with all of the requirements that I incorporated for the direct analysis procedure according to the AISC 36016 Chapter C specification. I can also move on to the design phase of my workflow and design my steel structure directly in STAAD.Pro Connect Edition.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.